to, so you had to be careful where you went. So there's a picture of it in one of my slides.
Oh, nice. Well, folks who have been just joining us, we have been learning about some of Guy Meadows' adventures in the past. He is our speaker tonight, and we'll be getting started in just a minute or two. And so we are, go ahead and put the first slide on, Guy.
Will do.
Yeah, and so welcome everyone for joining us. This is, I'm having so much fun with this, this webinar series. And what was I gonna say? So we're gonna wait just one more minute and start on the hour. And then, as you know, these are weekly webinars, Monday evenings at 6 p.m. and they are featuring a whole variety of different kinds of engineers. I almost call them flavors of engineering. Tonight and then also next week, they're going to be two different speakers focusing, who are mechanical engineers, who actually are quite expert on with matters regarding sound. So tonight, Guy will be talking about sonar images, actually, that can be created in the depths of the water. And then next week, Andrew Barnard will be talking about acoustics. Actually, he'll be talking about how to make things quiet. And so that's kind of where we'll be going over the next 2 weeks. So we're over 100 attendees. That is fantastic. And I recognize some names. Hi, Alan. Hi, oh, lots and lots of friends out here. Thank you, everyone, for joining us. It's really, really fun to see everyone, to see everyone's names. I think my sister's on. Hi, Ellie. So before we get started, I wanted to have another serious note and to once again acknowledge the heartbreak that we are witnessing being brought to the surface of our consciousness all over the nation and even across the world. Heartbreak triggered by the murder of George Floyd on May 25th in Minneapolis, which was a tipping point, it seems. Well, I want you to know that Michigan Tech stands together as a community, rejecting all actions that are steeped in racism or any other form of hatred. These actions do not align with College of Engineering values, which are leadership, integrity, impactfulness, inclusiveness, and excellence. The College of Engineering, along with the American Society of Engineering Education, believes that diversity and inclusiveness are essential to enriching educational experiences and innovations that drive the development of creative solutions in addressing the world's challenges. I am personally committed to diversity and inclusiveness and equity and anti-racism. There is much work to be done and we all have a part to play. In Tech Today, June 8th, 2020, there is a call to action article outlining Michigan Tech resources and initiatives. I encourage you guys to read it, and you can find it on mtu.edu/ttoday. And so before I introduce Guy, I have a quick note. I've been having a couple of emails from alumni who are curious about the COVID-19 research and preparations that we've been doing here at Michigan Tech. And so at the end of the Q&A, I've identified two of the topics that I will brief in a sort of short slideshow, maybe another 5 minutes of length. So if you're still here at that time, I am happy to do that with you. All right, and so now I'd like to introduce this evening's speaker, Guy Meadows, Dr. Guy Meadows, who joined the faculty, sorry, I'm gonna start from the beginning. He is Michigan Tech Mechanical Engineering Professor Guy Meadows. Guy is the director of the Great Lakes Research Center, and he was also the founding director of the Great Lakes Research Center. I think I just said the same thing twice. He is the Robbins Professor of Sustainable Marine Engineering. And so upon graduation from Purdue University in 1977, which is where you got your PhD, right, Guy?
That's correct.
All right. Guy joined the faculty of the University of Michigan, where he then served as professor of physical oceanography for 35 years. And then he joined us at Michigan Tech in 2012 to establish the Great Lakes Research Center as its founding director. His lifelong objective is to blend scientific understanding and technological advances into environmentally sound engineering solutions for the marine environment. And I guess that's a play on words. They're not just sound solutions. He uses sound in the form of sonar. And so, Guy, why don't you go ahead and take it from here? If your audio cuts in and out, I'm just going to wave, and maybe you can see me, and you might have to slow down.
Okay, thank you. And thank you, Dean Callahan, for that wonderful introduction. Did you want to say anything here?
Who?
Did you want to make a comment on this slide?
If we lose you, you can join us on Facebook Live, or you can try to kind of get back in. And so you would search for Michigan Tech College of Engineering, or you can go directly to that link. Go ahead, Guy.
Thank you. So it's an absolute pleasure to be with you this afternoon. It's a wonderful day here up in the Keweenaw Peninsula and on Lake Superior. I welcome you all and hope you are all well during these difficult times. As you heard a little bit about me, my bachelor's and master's degrees were both from Michigan State in mechanical engineering. I majored in heat transfer, fluid mechanics, and applied math. I worked with a professor as an undergraduate, and I strongly encourage all of our young students to spend that first year at college looking around and finding where your passion really lies. And for me, that happened in my sophomore year. I went to work with a professor at Michigan State that was doing studies in the water, large experiments in Lake Michigan for the Office of Naval Research on how waves broke across natural beaches. And as they say, the rest is history. I followed that professor to Purdue University for my PhD degree. And then right out of college, I was hired by the College of Engineering at the University of Michigan and spent 35 years there in the Atmospheric, Oceanic, and Space Science Department and the Naval Architecture and Marine Engineering departments. Both are in the engineering college at Michigan. And then fortunately, I had the opportunity to come here to Michigan Tech in 2012 and start another career in helping to begin the Great Lakes Research Center, which is an enormous commitment on the part of Michigan Tech towards the Great Lakes. And I respect the university greatly for doing that. But this career has allowed me to do lots of really cool things in the water. In the upper left is a picture of the Hydrolab habitat that was run by NOAA, the National Oceanic and Atmospheric Administration. I had an opportunity to spend a week living on the sea bottom, doing very detailed experiments that you could not do any other way. The picture on the lower left had the opportunity to survey extensively water bodies in Alaska, both in the Bering Glacier, which is pictured there, a glacier the size of the state of New Hampshire, and also on the North Slope of Alaska. In the upper right-hand corner, we have now a network of coastal monitoring buoys throughout the Great Lakes. Those were designed in my laboratory at University of Michigan, and we transferred that technology to a Michigan boat building company who are now building these buoys and making them available everywhere. But what we're here tonight to talk about are the two pictures on the bottom. The one on the left is Ivor, our fully autonomous underwater robot, and the one on the right is one of our small remotely operated vehicles that you control from the surface with a joystick, and we like to call it the ultimate video game because when you run into things, things break. So it's real reality. What's really unique about Michigan Tech is we don't just let students look at our fancy equipment, we make them use it in their classes. The upper left-hand picture is a picture of the university's research vessel, the research vessel Agassiz, with my class on board, and we're going out to program the fully autonomous vehicle, which in the upper right-hand corner is being launched by 2 students. That's a very expensive piece of equipment, and we teach you how to properly use it and properly program it so that it actually comes back to us at the end of its mission, which is a really important part. We also teach students how to operate the underwater vehicles, and you can see a student happily doing that. And our most recent high-tech addition in the mechanical engineering department here at Michigan Tech is a computer-controlled wave pool, and you can produce reproducible waves that look just like you would experience in nature. So those are tremendous opportunities to get your hands wet, no pun intended.
Well, and I will point out that that is at the bottom floor of the meme in case it springs a leak.
Ah, yes, it is in the bottom floor. So that's an important issue. So the ocean is a very noisy place, and the Great Lakes are a lot quieter than the ocean, but any body of water is very, very good at transmitting sound. The speed of sound in water is about 4 times the speed of sound in air. So sound travels very fast. But the ocean, there is tremendous sources of acoustic energy that is propagated into the ocean. A lot of that is made by humans. In exploring the ocean is noisy with active acoustic devices, which we'll talk about. The machinery of propellers and boat engines. I'm sure many of you put your heads underwater in local lakes and can hear the noise generated by boats. The wind, waves, rain, all make noises of different frequencies in the ocean. And then the things that live in the ocean are very noisy. Some are passive listeners, others are active communicators, like the whales and dolphins. They use their noises not only to communicate, but they can actually form acoustic signals and look for prey and understand what signals are bounced back to them and do amazing things with that information. So what they are is essentially acoustic remote sensors. And by remote sensing, we mean you're able to learn something about an environment in a place different than where you're located. So there's 2 types of remote sensing. Actively remote sensing, which is where you illuminate the target with energy that you create. An example might be is you go into a basement with the lights out and you have a flashlight and you shine the flashlight and learn about your surroundings. You're not touching your surroundings, but you are remotely sensing that, and you're doing that in an active way because you are shining the illumination on the targets that you'd like to illuminate. The other way to do that is passive acoustics. That's simply to listen. Some of you young folks may have heard from your parents that if you would just be quiet for a minute, you could learn a lot. Well, it's putting that into action where you are underwater and passively listening. So we're going to look at a couple examples of both of those. I've got Sean Connery here, who was the first James Bond, and is a really, in older age, is a really excellent submarine commander. So here's a little excerpt from Hunt for Red October, and it's an example of active acoustics. They're going to make an acoustic noise and try and determine the range to the target. And that would be exactly the same as you might do with a fish finder from a boat.
Re-verify our range to target. 1 ping only.
Captain, I just...
Give me a ping, Vasily. 1 ping only, please.
Aye, Captain. Oh, what the hell?
All right, so that was an example of active acoustic sensing. They're determining the range to the target by sending a pulse of of acoustic energy, timing that very carefully till it hit the target and the return signal back to their vessel. So that's how we do mapping of the bottom of the ocean or of the Great Lakes, is by sending pings at certain frequencies and measuring the time it takes and hence the distance, knowing the speed of sound propagation in water. All right, everyone needs to turn up the volume on your computers right now, because we're going to do a passive. We're going to learn as much as we possibly can by simply listening. So I have a sound here that I want to play for you, and I'll do it more than once because it's a little hard to hear. So turn those volumes up now. All right, here we go. All right, I'm going to do it again here. Listen very, very carefully to all the tones that you hear. And finally, one more try to hear that. Okay, now it's time for a little quiz. I think we have some questions for you to answer here. So, question 1. What made the sounds you just heard? Was it A, a bunch of coins, B, a bunch of keys, C, a bunch of sticks, or D, a bunch of cards? Oh,
Well, there seems to be a sound winner. There seems to be a pretty solid winner, Guy. What do you think?
It sure is. I think it's time to move on. A bunch of keys. You guys are good. All right, let's see here. Let's see what else we might be able to guess at. Go ahead, Dean Callahan.
How many were there? And was there 1 or was there 4 or was there 6? All right, and very few people are answering 1, but it's either 4 or 6, Guy.
Yep,
You're
looking good. All
Yeah.
right, one more question.
Oh, and that's this one. This one, you know, as a material scientist, I'm pretty sure everybody's going to get this right, because we know what if they were keys, we know what they were made of, right? And so the choices were metal, plastic, wood, or rubber relative to materials, and we're at 100%. So I think, yeah, I don't know if you taught them that or that was, you know,
I think they
prior
just
knowledge.
a really good class. I mean, 100% on your first college poll. I think that's pretty good. All right.
100, yeah.
All right, let's see what that is. So what we did is try to understand what, where, how many, and composition. And you did an excellent job. Here is the answer. 1, 2, 3, 4, 5, 6 keys. So 4 was a good choice, but you got it right, 100% right. So acoustically, we can learn a lot of information. So we're going to go on a little visit here. Michigan Tech is located there where the Husky is, up in Central Lake Superior. Beautiful, beautiful place. But today we're going to go underwater and visit 2 other places. The one on the right underneath the circle, the Thunder Bay National Marine Sanctuary, the only national marine sanctuary in the Great Lakes, right offshore of Alpena, Michigan. And then the circle to the upper left of that, the Straits of Mackinac, which is the confluence of Lake Michigan and Lake Huron, an area that has very, very strong currents propagating through. So if we're going to be an active remote sensor, it really helps if we can control the geometry. And that's the tremendous advantage that doing this with an autonomous underwater vehicle provides for us. Because the fully autonomous vehicle, our Ivor, we can program it exactly where to go, how to be oriented when you get there, what altitude from the bottom would give the best acoustic picture, how deep below the surface to stay, all those things. As we send Ivor out, it can operate for up to 8 hours without any human intervention. And again, it just depends on applying the proper programming to have that vehicle do exactly what you'd like. Well, a clue to that is these beautiful Getty images of the desert at sunset. So the sun is illuminating the targets. In this case, on the picture on the left are camels. It's near sunset, so the sun is very close to the horizon. And on the right-hand side are the shadows that are produced by those camels. And those shadows contain almost as much information as the camels do themselves in the photograph. So keep that in mind, and that's what we're trying to achieve on the ocean bottom with our active acoustic sonar system. But what we're trying to do is to set up the geometry so that we can get spectacular sound images, just like these spectacular visual images. So this is Ivor. It is a 3rd generation, fully autonomous underwater vehicle. We pre-program it, or we have our students program it. We tell it where to go, how long to stay there, how to move around underneath the water surface. And I'm going to show you a little video. It has a very precise navigation system associated with it. But keep in mind, once it leaves the water surface, GPS and all the fancy things we use for navigation are no longer possible. Those radio waves do not travel below the water surface. So once Ivor gets lined up, and here we are in the Straits of Mackinac, the beautiful Mackinac Bridge, it is turning now, it's lining up on its line, and in a minute here, it will begin its dive. It's getting fully oriented. We're following it in the boat. You'll see its fins flexed, and it will point down. It will dive down across the Straits of Mackinac. It gets as deep as 300 feet of water in other places.
Looks like he's actually using flippers, but he's not.
Nope, it has a propeller in the back and is a very accurate tool for this type of purpose. Along the side, these black bars that you see along the side are the acoustic lenses that form the beam that allows us to light up targets just like you would with a flashlight. So this again is the perfect picture we're looking for, but we're looking not at camels, we're looking at the ocean bottom or the lake bottom. In this image, the white things that you see are the camels, the black things are the shadows. So the shadows are extremely important in acoustic imaging. And here's an example of the types of imagery that we collect with Ivor. This is a upside down motor vehicle. You can see the 4 wheels shining up very brightly. You can see the muffler and the drive gear underneath the car. And you can see a shadow of the car across the lake bed. So this is not a visual image. This is a sonar image, much like you'd see in a hospital from a sonogram. The pot marks all across the bottom are fish nests. So again, we know all the geometry. We can measure the length and the width of the car and whether the muffler pipe is in good shape or not.
How deep was that?
That's only in about 30 feet of water. That's a test bed on the East Coast where Ivor is built, and we send Ivor back and forth a couple of times a year to have its systems tuned up. It's a commercially available vehicle that you can purchase. We're now in the Thunder Bay National Marine Sanctuary offshore of Alpena, Michigan, and we're at a depth of about 240 to 260 feet below the surface. And these are 2 sonar images taken by Ivor of historic shipwrecks that are in the sanctuary. The one on the left is the John J. Audubon, which sank in 1854, a three-masted sailing schooner here on the Great Lakes. You can see tremendous resolution on the deck of the schooner. From the sonar image, you can see a wonderful shadow cast across the lake bed behind the wreck. You can see in the shadow that the aftermost mast on the vessel is still standing mostly upright by the length of its shadow. And then all strewn across the bottom, in addition to the forward mast laying out there, are a whole bunch of little sticks. And that is the cargo. The cargo of the John J. Audubon was railroad rails. So those are the iron rails that the train rides upon. So again, you can see that this is a very high resolution sonar image of debris on the bottom.
And what took it out? Was it a storm, you think? Or
yes, this one sank in a storm. Very good point. The one on the right, however, sank in a collision. It is the Typo. It sank in the late 1800s in the fog, and the area off of Alpena is a convergence of the traffic lanes for ships, even back in the 1800s. And it's an area just like Lake Superior that is notorious for very dense fog. Well, this being in the late 1800s, the Typo was rammed in the back by a steamer, one of the newer steamers on the Great Lakes. The cargo of the Typo was coal, and you can see the coal has spilled out of the back of the ship. The forward mast is almost totally intact, and you can see a very long acoustic shadow across the bottom from the forward mast. The second mast is much shorter, broken off perhaps a third of the way up, and the back mast where the collision occurred is laying crossways across the ship there on the lake bed. So again,
so I have two questions.
Resolution sonar. Yes, ma'am.
Well, what happened to the other half of the ship? Did anybody find it?
It was mostly destroyed in the collision, and there was crew members on this vessel, and because the back was essentially ripped off in the collision, and as water rushed in, we suspect the ship tipped up with the nose, the bow upward and the stern downward, which caused the coal to spill out. But it also there is unfortunately a body buried in that coal. So there was loss of life in both of these accidents.
And did the steamer do better than it?
The steamer, I believe, also sank not too far away. So very bad day. This was a previously undiscovered wreck. Also in the marine sanctuary, a little further offshore in about 300 feet of water. So in these depths, the other two wrecks that we saw have been both explored extensively by technical divers. This wreck, the Choctaw, again, is getting deep enough where it's very, very dangerous to go that deep for humans, even as experienced technical divers. So it's a place where an autonomous vehicle is ideally suited. For autonomy on the oceans, we think those vessels that are fully autonomous and vehicles like we're using here are best used for operations that are dull, dirty, or dangerous. And certainly this fits that category. So this boat is one of the first steel-hulled freighters on the Great Lakes. It sank in the very early 1900s. It was lost and not discovered until a couple of years ago. And they asked us to come in and provide very high resolution sonar images so the marine archaeologists would be able to identify what ship it actually is. What is unique about this ship is it's about 300 feet in length, but the first 100 feet of the ship is stuck in the mud in the bottom. So it's like a lawn dart with the stern about 60 feet above the bottom. Both images are just different views from Ivor with its advanced sonar system of the same ship. You can see in the one on the right that the propeller and rudder is very visible in the sonar image, the hard target return, as we call it. And in the picture on the right-hand side, the shadow very nicely shows the rudder and the propeller. So two different views of the same ship, both revealing very detailed but very different information. And you can see a pretty extensive debris field around the vessel. But it's just amazing to me that 100 feet of that boat is stuck in the mud, and you can see the impact crater, particularly on the right-hand side of where that harpooned itself into the lake bottom. Finally, this is some work that we have done in Straits and Mackinac. Ivor does not see directly below itself, so that dark streak in the very center is the blind spot underneath the side scan sonar, but it does map about a football field either side of the vehicle. And on the left-hand side, that object, the long straight object protruding outside from this pile of material is one of the Enbridge pipelines that crosses the Straits of Mackinac. So up until we arrived on the scene with Ivor, Enbridge was required by the Department of Transportation to measure unsupported lengths of the pipeline once every 3 or 4 years. They did that with hard hat divers and a tape measure, essentially, to measure unsupported lengths and then support those lengths that were in exceedance of their agreement. With Ivor, we developed mechanisms to do that autonomously with the underwater vehicle, and it takes us about 4 hours to do the pipeline all the way across the Straits of Mackinac rather than once every 4 years. So we can do that as much as every other day if that was necessary. But what we do is we keep track of areas that are eroding and areas that are depositing sediment across the straits. And as I mentioned earlier, the currents in the straits are constantly reversing and are extremely powerful at times. We have one of our environmental monitoring buoys in the straits, and that's available to the general public. It's buoy 45175, and you can go there anytime and look at the waves, the winds, the temperatures of the water, and most importantly, the variation of current from the surface all the way to the bottom. So with Ivor, we developed ways to measure, again, knowing the geometry, looking at the shadow behind the pipeline. Since we know the elevation above the bottom, we can measure the length of the shadow and determine the height above the bottom that the pipeline is. And we've transferred that technology to the marine community, and they are doing that now on their own. So Ivor has played an important role, we believe, in helping to keep the straits a safer place. And then I want to thank you, and I will be around for questions, but Dean Callahan has something to announce here.
I do. I wanted to make sure before as you start, so at this point you can start typing in your questions in the Q&A field. And while you're doing that, I wanted to point out our next speaker, who is Andrew Barnard. He is going to be talking about ways to kind of keep things quiet. And I also wanted to ask if anyone out there was interested in sponsoring one of our Husky Bites webinar. And if you are, contact Bryant Weathers, who is one of our hosts here. I should acknowledge and thank the hosts, actually. Thank you, Bryant. Thank you, Sue. And that's Bryant's email. And all proceeds from these sponsorships, 100% of them, without any sort of tax or fee, goes to support students. We feel that students are going to probably need a little more help than they normally do as a result of what's going on in the world with the pandemic. All right, so let's go ahead and go to the next slide, and we'll start taking Q&A. And so Guy, you can, there we go. All right, and so let's take a look at the Q&A. And so Guy, you should be able to see these too. And so we have a first question coming in, which is, for people who are at the beginning of their major, selecting their major and career, what advice would you give them?
Well, my advice is to spend your first year looking around. In order to be successful and be happy, you have to be passionate about what you're doing. So I highly recommend you visit different departments. You know, all universities are very open places, but Michigan Tech, I think, is probably one of the most friendly places I've ever been. So you are welcome to cruise through any department, to attend any department seminars, talk to faculty members, talk to students, get involved in student organizations, and really spend
Guy's starting to sound like a robot. He'll come back and he'll start talking really
I'm
fast.
sorry.
We lost you for a minute there, but I think the gist of what you were saying.
I'm sorry.
No, it's okay.
Right.
So our next question is, how does sonar or sound waves get converted into a visual image, especially with vivid colors and showing texture to a certain extent?
So we choose the phrase that we transmit the sound so that we get that tremendous detail. It's a very complicated process. The acoustic lenses, there's one on each side of Ivor that point down slightly from horizontal. They are, inside each of those is actually 10 lenses that all work together to form a very accurate beam. So the beam is transmitted horizontally out across the bottom from Ivor, and the echo comes back equally complex, and that's all digested within the electronics on board the sensor. So the color that you see is false. We could make that different shades of red or green. The copper kind of color really shows the texture, as you pointed out in your question, very well. We transmit at 600 kilohertz and 1600 kilohertz. And you're looking at there the very high resolution return from shining a light at those very high frequencies on the image, an acoustic light.
Excellent. All right. And so let's see. I want to go to this question, which is, which engineering major is best if you want to work with underwater robots?
Well, of course, mechanical engineering.
I figured you'd say that.
No, but seriously, there is so much work to be done underwater that any science or engineering major or policy major, because of the issues facing the oceans and Great Lakes, any discipline has a place. So when I'm being really obnoxious, I say we do the engineering for the 3/4 of the planet that's covered by water. So there is a tremendous opportunity, since there is so much water on this planet of ours that needs to be looked after and cared for, that any form of engineering can find a home working in what we call the marine environment.
All right, so this next question, I'm going to ask for help from the audience. And so you can tell us the answer by typing in a Q&A, which is the answer, because I don't think Guy or me knows the answer to this question. So, and this is, where can I buy MTU logo fabric? I have multiple people that like to sew and can't find it to make things. So we're going to wait for the answer for that, and we'll get back with you, Don, on that. And so the chair of electrical is curious about what causes the pipeline to become unsupported.
What causes the pipeline to become unsupported is the strong currents that have always flowed through the Straits of Mackinac. They are able to move sand and larger particles back and forth between Lake Michigan and Lake Huron as things slosh back and forth. The Straits of Mackinac, when the Great Lakes were formed, was actually a river that connected two separate lakes, one the pre-Lake Michigan, the other the pre-Lake Huron. So that river valley still exists through the center of the Straits. Between the two spans of the Mackinac Bridge, the water is as deep as 320 feet. In the area where the Enbridge pipelines are. It's as deep as about 260 feet or so. So that river valley runs through the center of that. You might recall that there have been two vehicles that have gone off the Mackinac Bridge. The first was a Yugo in a very windy, stormy night. And I had just returned from my week underwater, so I was very up on decompression and how to return to the surface after being on the bottom. So I was asked to help the Michigan State Police dive team with that recovery in terms of supervising parts of their decompression. And those men and women on the dive team, in order to spend about 5 or 6 minutes on the bottom at 300 feet or so to do the recovery of the Yugo and the woman involved, had to spend about 2 hours returning to the surface. So it was very, very dangerous operation. The second vehicle was a full-size Bronco that was ruled a suicide. But again, by that time we had a underwater vehicle, and we're able to do, that was in February, we're able to do that entire recovery of the vehicle through 2 feet of ice without putting divers in the water. We did it all with what is now autonomous or surface controlled recovery techniques.
So this next question asks, are projects like what you were doing with the Ivor only worked on by mechanical engineers, or do other types of engineers get involved?
No, absolutely. All types of engineers get involved. I mean, there are 2 dual core processors on board Ivor to control its sophisticated systems. So computer engineers, electrical engineers, light and sound engineers, all types of engineering types. The materials, material engineers, it's a corrosive environment in the ocean and much less so in the Great Lakes. But again, the types of materials that it is involved with, structural engineers, the pressure at 300 feet below the surface, either in the Great Lakes or the ocean, is tremendous, roughly 30 atmospheres. And, there's just all kinds of engineering that go into these vehicles. It's not only the creation of the vehicles, but it's the maintenance and operation of the vehicles also to be able to run them efficiently. So all types of occupations are involved.
So Paul asks, have you surveyed the Edmund Fitzgerald?
We have not. We had an opportunity once to do so when I was at University of Michigan. But that is such a recent wreck that, out of respect for the living relatives of the 29 crew members that were lost, it is their grave site. We decided with the university that it was not appropriate. So we have not visited the Edmund Fitzgerald.
All right, and Cameron asks, what camera is used to get the shadows?
That's not a camera. That's from the acoustic illumination of the target. It's just like a camera. It's just like you shined a light on those shipwrecks, but it is the shadow that the acoustic waves can't get to that part because they've hit the side of the ship and they've bounced back to us. So just like there would be a shadow with the flashlight, there is an acoustic shadow on the backside of those shipwrecks. And that's why we try to set up the geometry to catch those really spectacular shots, even though it's not like light with a camera.
All right, and this next question is the sonic receiver on the boat or on the Ivor?
It's on the Ivor.
So everything's on the Ivor.
Everything's on the Ivor. The Ivor sends the signal and then waits for the return. Very, very quickly.
Very interesting.
Doesn't wait very long.
So do you have any shipwrecks in line to go and visit next?
Oh, that's perfect. The biggest mystery in the Great Lakes is right here in Lake Superior, and it's a 102-year-old mystery. So during World War I, at the end of World War I in 1918, the French government contracted with a Canadian shipbuilding company on the North Shore of Lake Superior in Thunder Bay, Ontario, to build 10 steel-hulled minesweepers for the war effort in the English Channel. 7 of those were built and completed and left the Great Lakes and went to join the war effort off the coast of France. The last 3, as you might guess, were finished late. They left in November, about 50, 60 miles off of coming around the tip of Isle Royal. They were hit by a tremendous westerly storm, just like what happened with the Edmund Fitzgerald. And the commander, who was on the lead vessel of the 3, signaled with light signals, because wireless communication radios was a new thing in 1918, to the other 2 boats to not go to Sault Ste. Marie as planned, but to come and hide behind the Keweenaw Peninsula until the storm passes. They lost sight of each other, the 3 boats. The commander on the first boat arrived finally to behind the tip of the Keweenaw for shelter, and assumed that the other 2 boats never received his light signals, and they would be waiting for him when the storm passed at Sault Ste. Marie. When he got there 2 days later, the other boats were never heard from. So we believe that they have been lost right off the tip of the Keweenaw. People have been looking for them ever since 1918 with no luck.
Oh,
Because the
wow.
water is very, very deep there, between 580 to 900 feet deep. And those it's the single largest loss of life in a shipping disaster for Lake Superior. 73 souls were lost.
Chris asks, have you ever been involved in a search grid type project like they did to try to find the Malaysian airliner?
Yes, but obviously on a much smaller scale. We've worked extensively with the Michigan State Police and still do, and we have done a number of searches with them, sometimes successful, sometimes not. But it is very time-consuming and tedious work. And one of the really rapidly evolving technologies in working in the ocean is autonomous surface vessels. And that is, they have matured to the point now where they can go for 7 days, 24 hours a day, and do that very rigorous grid pattern searching. And as you bring up with Malaysian Flight 370, the company that did the most recent search had 8 of those involved in the search, 4 on each side of the control ship. So instead of doing 1 line at a time, you're doing 9 lines at a time. So it's really becoming important, the whole field of autonomy. So those of you that are interested in autonomous systems and doing the software and the control hardware to develop those, I highly recommend that you give that serious thought. It's a really rapidly changing industry right now.
Well, and so I don't know if you know this, but it is World Ocean Day today, and this is brought to us by an anonymous attendee. So happy World Ocean Day to everyone from this attendee. And then from that, I want to go to Larry's question. What is the depth capability of the autonomous vehicle? So could it be used to explore the very deep parts of Lake Superior?
Our Ivor is limited to 100 meters, roughly 330 feet. The one that we worked with the state police to buy, and they have one very similar to ours, but they were able to get the extra benefit of having twice that depth. So that one can go to 200 meters or 660 feet roughly. The deepest part of Lake Superior is 1,333 feet. Our remotely operated vehicles can go to 1,000 feet. There are Ivor-like vehicles that can easily go to the depths of Lake Superior greater than 1,000 feet. But again, the deeper you go, the more it costs. So we're really happy with our Ivor, but yes, other companies are making very deep capable autonomous underwater vehicles.
And so Paul asks a question. So in addition to the imaging, are traditional materials science type non-destructive test methodologies also in use on the Enron type pipelines or ships? Do you know? And if so, what are their effectiveness?
I don't know the answer to that.
Yeah, I don't know either.
You can hang pretty much anything on an Ivor type vehicle. We have recently built one for the U.S. Geologic Survey that is designed as a camera ship. It has stereo imaging, high-speed cameras, and a lot of smarts on board to look for invasive fish species. So there's, you can design these vehicles and outfit them to do many different tasks. Ours, we have been mostly interested in doing bottom mapping and detection of really precise measurements. And that's why since sound propagates so well in the water environment, that's why we've chosen to configure ours as a sonar ship as opposed to a camera ship.
And so we've got a couple.
With one more comment, if I may, we do have a very nice camera on board and a strobe light. And throughout the missions, Ivor takes a picture once every second.
We've got a couple people asking, they don't, and I'm a little fuzzy too about, you mentioned a pick with a shadow. How does sonar have a pick with a shadow? So this relationship of sonar and the shadow, I don't know if you can explain it without a whiteboard.
Because we're so handicapped here by being remote. I can't stand up and do all my gestures either like I normally would. So we send out this beam of sound energy, and it propagates, as a series of waves towards the structure on the bottom. Some of those waves hit the side of let's use a shipwreck, for example, hit the side of the shipwreck. Some of those pass over and hit the ground at, the same angle that they were incident at the shipwreck. So they hit the ground behind the shipwreck at some distance. Well, that difference between the waves that hit the side of the ship and bounce back to us versus those that continue on past the ship and eventually hit the ground and come back to us, that difference between the two in the absence of sound is just like the absence of light in a visual shadow that you're used to seeing. So it's exactly the same principles. It's just we're not shining a physical light, we're shining acoustic energy at the target. I hope that helps.
That was a good explanation. Yeah. Kirsten asks, she says, you mentioned that the buoy in the Straits is accessible to the public, and how would the public access the info?
So go to the Michigan Tech website and then find the Great Lakes Research Center, find our website, and right below the big picture of the building is a picture of a boat and a buoy. Just click on the buoy and it'll take you right there. It will light up a whole bunch of buoys across the Great Lakes. Any of those that are lit up in yellow are a buoy that has reported in the last 10 minutes. So we set our buoys to report every 10 minutes. You can click on that buoy and you'll be at a wonderful website that will tell you way more information about that buoy than you ever wanted to know. So again, give it a shot. And if you have trouble, send me an email and I'll help you through it. But you're more than welcome to explore to your heart's desire. It's designed to be open to the public. If you're really into it, there's a place to get data at the bottom, and you can select what you'd like to have reported for any particular days going back as much as 6 years. And it all comes out in a gigantic Excel spreadsheet. Keep in mind that the buoys are not in the water during the winter months. And because of the coronavirus, we were slow in getting the buoys back out. So the Straits of Mackinac buoy has been in now for about a week and a half. So there won't be any data before that time for this year, but there is all of last year's, the previous years, and the previous years instantly available.
So we have two questions that are related to each other from Saida, asking, would you please talk about ROVs and pigging systems? And one of the problems in pigging systems is how to kick the pig into the fluid. Do you have any solutions? So I don't know what that means.
I don't either. I'm sorry.
Okay. I thought I would pass it along.
Thank you.
And then, so perhaps this is from an anonymous attendee. Are there any particular benefits of using underwater vehicles with sonar as compared with the surface ships with powerful sonar?
Yes, and that's an excellent question. So when we're looking for something like the French minesweepers, we do a kind of a layered search pattern. So we start out with a surface ship and we try to, find a target because the surface ship can travel relatively fast. It's relatively comfortable and you can cover very large areas. But if we get some hits that look potentially interesting, then the next layer is we send Ivor to get with its fancy sonar to be able to swim down and be as close to the shipwreck as our depth limit allows us to be, and to try and get some of these spectacular images so that we can see what we're dealing with, what sort of structure, if the mast is still up, is there rigging and cables and those kinds of things. And then the third step is to use the remote operated vehicle where we can actually go down with real video cameras and lights and illuminate the target that way. And to identify the ship for sure, we actually swim around to the back side of the ship and see if we can read the name on it. So it's that simple. But on other ships, that once we know that they're clear of obstructions, because getting the university's equipment stuck and not getting it back is bad. But once we're sure that you're able to get back safely, we've swam through hatch covers and down into the holds of the ships and looked at things that people haven't seen for, in some cases, well over 100, 150 years and stuff. And I will say there is one ship, and I'm not going to say where it is or which one it is, but we saw big oak casks of some appeared to be filled with some form of fluids. Preserved.
Maybe it's whiskey.
And you know that the bottom water of the Great Lakes is at 4 degrees centigrade summer and winter. So it's always at 39 degrees. So whatever was in those casks has been ideally preserved for 150 years.
Triple aged, triple cast something.
Yeah.
So a related question, I was just reading this. So it's about, does Ivor and other autonomous ROVs have code to deal with getting tangled up or stuck somewhere in the water, or what happens? Do the robots alert the humans and a human has to go rescue it, or what?
These are just excellent questions. This wonderful audience. Yes, they do. So we have limited things that we can do. And again, we have no communication with Ivor once it leaves. So all this stuff has to be anticipated before in its programming, as the person asking the question indicated. So we have a forward-looking sonar on Ivor that looks for objects that Ivor could run into. And we have two choices. We can have it, if it detects an object in front of it, we can have it pitch up, or we can have it pitch down. So if we're relatively swimming close to the surface and it detects an object, it might be the side of another ship or something, we typically program it to ship. We select the option to pitch down and try and swim under it. If we're doing a survey close to the bottom, we would choose the other alternative, and that is have it pitch up and try and swim above it. If it does run into something or get stuck, it will try to back itself up. It will go
Mhm.
into reverse and try and free itself. But we've never encountered that type of encounter yet. So we haven't tested that one.
All right, so this attendee asks, how did you know you wanted to study engineering?
Growing up in Detroit, I was, a victim of the automobile industry. It was really important for kids when you turn 16 to learn how to drive and to get your driver's license as soon as possible. I really enjoyed taking things apart and half of the time being able to put them all back together again. I had, as I said, two uncles and a couple of cousins that became engineers, so I was around engineers. I'm a firm believer that you can't have enough mathematics no matter how much you have. So I always enjoyed math, and those things all came together for me as an engineer. And then when I figured out in my sophomore year that you could be an ocean engineer, that was just the best of both worlds for me. So I really enjoyed doing it, learning about it, and that has continued to this day. I think retrained myself 5-10 times now, and I'm just really excited to keep tinkering with things.
Well, and mechanical engineering is one of these really solid fields from which you can do that, and then if jobs dry up in that field, you have that basic credential of being a mechanical engineer, and that's the beauty of having kind of like a less boutique-y kind of degree name at the bachelor's level, at least.
Yes,
All right, go ahead.
We've had tremendous success from the classes that we've taught here that are ocean engineering related. We've just had 2 students be hired by General Dynamics Electric Boat to help design our nation's next submarines. Something we're very, very proud of.
Very interesting. All right, we've still got about 10 questions left, and it's on the hour. And I just wanted to mention again that I want to thank all of our attendees, and Guy's going to stick on and keep answering questions. We still have about 100 participants, Guy, which is pretty impressive. After the Q&A is over, I'm going to present, for those who might be curious, a couple of the COVID-19 related research areas that we're going to be doing. But it's okay if you need to leave ahead of that. I understand. It's because alumni have been asking me about what we're doing relative to the COVID-19. So I'm going to, this is from Mel Visser, one of our alumni who sponsored us last week, actually. He asks, what is the rate of sediment accumulation in the area of the shipwrecks?
Hi, Mel. It really depends on which wreck. The accumulation in the deep parts, these very deep wrecks, 250 feet to 300 feet, is very, very slow. So we have not noticed any accumulation of sediment around those deep wrecks. The shallower the wrecks are, the more sediment motion there is. And once you get into the range where light penetrates into the lakes, which is, somewhere around 50 meters or so, then the zebra and quagga mussels has been a huge deterrent, and in some ways has really destroyed the looks of these wrecks. So to see a pristinely saved wreck that has lasted for 100 or 150 years to suddenly become encrusted with this invasive species is really heartbreaking. So rather than sediment in our deeper experiences, it's really been the originally zebra mussels and now the deeper living quagga mussels that have changed the view of the wreck and what you can see visually.
All right, and now we have a question about what is your favorite part about working at the Great Lakes Research Center?
The ability to have a job where, first of all, your building sits right on the water. It's a spectacular building, and as I said before, a huge commitment on the part of the university to towards the Great Lakes and understanding this valuable resource. But then the ability to be able to work on the water, there's nothing better in the fall than cruising on the research ship down to either North Entry or South Entry, which is about an hour-long ride, looking at the beautiful colors and the wildlife and the eagles. And I mean, it's not fair to call it work.
No, I know. We live in an extremely beautiful place. I'm glancing out my window. We actually still have snow on Mount Ripley, though. Just a little bit, but there's still snow. And so I think this question from Michael is about, it asks, would the autonomous robot work in the ocean, which you said was louder, I think as compared with in one of the freshwater lakes. And so how does it do in the ocean, basically?
It does really, really well. It's designed for ocean work. We get every once in a while a terrible reminder that, one, we get away with murder because we don't have the corrosion issues that salt water does. So from that, it's a benefit. But every time we send it back to its manufacturer, which is on the East Coast, and they do their work and tune it all up and test it before they send it back to us, we got to remember that we have to reballast the vehicle. That means we have to change its weight because it floats better in salt water than it does in freshwater. Salt water is more dense than freshwater. And we learned that lesson the hard way. We forgot to do that one time, and we sent it out, got it back, and we're excited to use it. And we sent it off the end of our dock at the Great Lakes Research Center to do our standard test mission. And it did it fine and came back, and you pre-program it to have a park point. So it will go there to the park point and park itself, and the wind and waves will blow it away, and it'll motor up again and come back to its park point. And it'll wait there for you until its batteries run out. So it's a tremendous feature of the vehicle. When it's done, you can be out doing something else and you'll know exactly where it's parked itself. Well, it parked itself, and because it was still ballasted for salt water, it properly sank. And so luckily we had the remote operated vehicles with the little grabber arms and stuff. So we were able to swim that down there and grab a hold of it and bring it back to us. But it's just one of those silly things that, the ocean will get you if you're not paying attention.
That is interesting. So Connor is curious about the pipeline. And so if it's exposed, what does the company do to solve the problem of it being exposed?
It's good question, Connor. The pipelines have always been exposed. So they were laid across the lake bed in 1953 when they were constructed and put in place. That pile of material that you saw over top of the pipeline, we think that was placed there when the pipelines were first constructed and put there to kind of hold them in place. So they've always been just laying across the lake bed in those places, but sediment is constantly moving. And some places the pipeline has become more buried, other places it's become less buried. So again, what is of concern is if the material erodes from underneath the pipeline and longer than 75 feet is exposed, then they get concerned about the pipeline flexing. So anytime that more than 75 feet or more is exposed, the company goes in and with divers and sets very fancy sawhorses to support that actually are saddle clamps that that go down into the substrate and with big screw anchors and hold the pipeline in place.
Yep. Interesting. Paul, who is one of our mechanical engineering alumni, I believe, mentions that a very rewarding part of his career was designing submarine listening devices called Sonar Buoys at Magnavox. They had both active and passive devices. So that's very interesting. All right, and then Roger Smith, who actually used to garden in my back garden. And Roger, I'm trying to replant the historic garden here. I've gotten pictures of what the house used to look like. So if you want to weed anymore, you can let me know and you're welcome to come weed. He asks, have you investigated the shipwrecks off of Keweenaw, for example, in Copper Harbor? Or
No, we have not yet. That is on our to-do list. We spent about a week last year looking for the French minesweepers, and we had some very good targets, but they turned out to be natural features and not shipwrecks. But no, there are some spectacular shipwrecks all around the Keweenaw. We've looked at a couple of them, but not in the detail that we would like to.
And Leonard asks, what shipwrecks have you investigated in Portage Lake?
Portage Lake. None.
None.
There is a wonderful little wooden barge left over from the copper industry, right down from the Great Lakes Research Center, right in front of Princess Point there, about 50 or 60 feet offshore. It's in tremendous condition and is the home to many, many fish. So we've looked at that very carefully, but we have not looked at any of the wrecks that I can recall in Portage Lake. If you know of one, let us know.
An anonymous attendee asks, are there graduate internships available in your group for master's or PhD students to do underwater robot work?
Yes, there are. So, that's how I got started. So, I went to work for a professor, and he was paying better than me being a cook in the dormitory. So it was, it's how I got started. So we work really hard in the Great Lakes Research Center to make as many opportunities for students at all levels to work there. And if you're incoming freshman, don't be shy. We really love incoming freshmen because we have you for 4 years and we can train you and keep you around and hopefully have you do things that you're excited about. So don't be shy if you're an incoming freshman.
I want to second
at
that.
all levels.
It's one of the strengths. It's one of the strengths of Michigan Tech is that we engage our undergraduates in research, and often they end up publishing a paper before they graduate, and it's pretty impressive. Be careful though; it makes you addicted to research, and then you end up, like Guy and me with a PhD and professors and stuff like that. You don't have to do that. I'm just saying it's not a requirement. All right, so we have the answer to what this pigging is. So in its simplest form, a pigging system consists of a solid projectile or plug, which is the pig, with a diameter slightly larger than the pipeline or tubing that is transporting a liquid. The pigging process introduces this pig into the pipeline and pushes it through the pipe, presumably to clear a blockage or to just kind of get the goo off the edges of the inside of the pipe. I learned something today besides about all these cool shipwrecks.
Yes, thank you for that.
Christy, and I think I recognize that last name, perhaps an alumna, asks, how does normal boating traffic affect ELF sonar, ELF?
ELF is a old system. In fact, our former university president is just retired. He was part of the original setup of the ELF system. The idea was to be able to communicate with submarines deep within the ocean by essentially rattling the bedrock, which is exposed here in the UP. So it was a very low frequency system, and one that, again, most boat traffic would have very little effect on, but very low frequency transmissions. And again, those low frequencies travel thousands of miles in the ocean environment.
All right, this is a last kind of weird question, kind of creepy question from Bob Carnhand, class of 1953. Has there been any assistance requested in Chicago River scanning in relation to the 1892 word, fair serial killer / Jack the Ripper?
No, not to our knowledge. We can see, we as I said, we've done a number of searches and recoveries, not rescues, but recoveries with the state police. And our sonars do see drowned victims below the water surface. We have, very high resolution capability. Similarly, we can see seeps, natural seeps, plumes of warmer or colder water coming out of, say, groundwater seeps that are below the surface. So we have the ability with the sonar to see things you might not think we normally could see. But we've not been asked to do any of those types of searches. There's a tremendous amount of infrastructure left in the Portage waterway from the copper mining history. So it's a very target-rich environment to cruise the Ivor just up and down the waterway and look at the sunken barges and rock carts and those types of things. It's an amazing field of materials.
All right, and this is our very last question. And Guy, you have answered 37 questions live at this point, and some of them were kind of doubles. So if we didn't answer exactly your question, it's because it aligned with an earlier question. So this last question is another one from Christy, and it asks, what kind of sonar work does the U.S. Navy do in Alaska?
I don't know the answer to that. I know that, there's throughout a lot of the ocean, there are test ranges established for military sonars. Sonars at high energy certainly can have effect on marine mammals. So there is a tremendous caution used these days in terms of sonar imaging in those areas. When we did some work in the Bering Glacier area, it's an area that's populated by seals. We had to make sure our sonars were very low energy sonars operating at the bare minimum, and to keep the noise in the environment to as absolutely low as possible.
All right, so Guy, that we got to the end of all those questions, and I want to thank you personally. I enjoyed so much. I was taking all these notes, and I want to look up all these shipwrecks, and I actually think I understand how sonar works now. And I've also recently rented the Hunt for Red October. I'm going to rewatch that. I have that on my queue. It was wonderful, absolutely wonderful to have you as our webinar guest tonight. And I thank you deeply. And so relative to our participants, I think we've still got quite a few on. And as I mentioned, I hope you can you guys see my screen?
Let me give you that. And thank you, everyone.
I've seized control from you guys, so you don't have to give it back to me.
Excellent.
And so, Sue, we don't need to tape this part. I did want to. So, are you seeing a slide that